Hi, everyone. I'm Joe Maglioka. I'm a virtual tutor here at the online ILC. I tutor all chemistry and biology classes and most math classes except the really high level ones. So, so I might see some of you throughout the semester if you come for a tutoring appointment. Anyway, well, today we are going to go through a workshop titled um, scientific notation, um, significant figures, and the metric system. And so I'm covering this as kind of an introduction to quantitative sciences, especially chemistry and physics, but even biology and earth sciences will cover some of this material. So let's see here. Can everybody see the PowerPoint? Great. Okay, I'm going to do F5. So, can you still see it? All right, great. So let me go back down to the F5. Unfortunately, I can't see your questions during when I do F5. Feel free to ask any questions in the chat, and so I'll have to leave the um I'll have to leave the PowerPoint though when I do that. So there we go. So as I said, this is titled Scientific Notation, the Significant Figures, and the Metric System. Introduction to Quantitative Science at Wake Tech. So this has three sections. Section 1 covers scientific notation. Section 2 covers measurement units in general and especially the metric system. And Section 3 covers significant figures, which is a very important concept to learn about when you're working with measurements. So my plan is that after each section, I'm going to leave the F5 view and answer any questions. So feel free to ask any questions in the chat as soon as you think of them, but I won't answer them until we get to the end of the section. Okay, so originally this workshop was just going to cover the metric system and significant figures. But I noticed a lot of not everybody has fully learned the concept of scientific notation in detail, and for the metric system, scientific notation is very important. So I wanted to start with a little bit of an overview of scientific notation, just to clarify and make sure everybody fully understands it. So what is scientific notation? So it's a method for writing very large or very small numbers so that's easier to understand. So I give it as an example here. You can pretty easily understand 0.75, 15, 974, and 8. I mean, you know what numbers they are and which one's biggest, which one's smallest fairly easily. But what about these numbers? It's a lot harder to just know what these are. Most people have to count the zeros before you know what these numbers are. So like this is 127,500,000 and 14 quadrillion, 14 quadrillion, 800 trillion. But you know you have to count the zeros to know what these are, and and you have to think about it before you can know like which one's biggest, which one's smallest. However, we can also write these three numbers as 7.5 times 10 to the negative 10th, 1.275 times 10 to the 8th, and 1.48 times 10 to the 16th. And with that, it's a lot easier to know what these numbers are and which one's biggest, which one's smallest. Already written from smallest to biggest, but anyway.
Hey, Jason, Joseph,
Yeah.
they're not seeing the PowerPoint change.
Oh, they aren't? Okay.
What?
Can you see it? Oh, can you see it now? I just won't do the F5 view.
Yeah, they can see it change now.
Okay, so you see what is scientific notation? Okay. Um, okay, great. So I'm just going to do it with this view then. Okay. So I'll give you a chance to look at this. So like I was saying, yes. So these numbers, so yeah, the bigger numbers, it's harder to tell what the numbers are without counting the zeros. These were the numbers I was referring to. But it's easier to know what these are if you write them like this. I guess this way I can highlight what I'm talking about. So how do you convert from standard notation, that's, these are all in standard notation. How do you convert from standard notation to scientific notation? So to convert from standard notation to scientific notation, numbers have to be rewritten as a coefficient multiplied by a power of 10. So it's like a whole number, or a number between 1 and 10, because in proper scientific notation, the coefficient is always between 1 and 10. And then that's multiplied by 10 raised to a certain power. So to convert a large number to scientific notation, you'd move the decimal point to the left until the number you have is between 1 and 10. And then as you do that, make sure you count how many places you move the decimal point. And if no decimal point is written, you can assume that there's one after the last written digit. And so now you have a coefficient. And the coefficient now must be multiplied by 10 raised to the power equal to the number of places the decimal place is moved to the left. Small numbers, that's numbers less than 1, can be converted the same way, but in this case, the decimal place is moved to the right instead of the left. And it's the coefficient is multiplied by 10 raised to the negative power of the number of places it was moved. So here are some examples with numbers that aren't quite so big and so small. So if you take the number 2400, there's a decimal point after the second zero. So we move it once, we would have 240. Twice, we would have 24. 3 times, we have 2.4. 2.4 is between 1 and 10. So that was 3 places. So in scientific notation, it's 2.4 times 10 to the third. Now for 0.00086, we move it to the right. We have to move it a total of 4 places to get a number between 1 and 10, which is 8.6. So in scientific notation, this number is 8.6 times 10 to the negative fourth. So once you have a big or small number in a scientific notation, it's easier to conceptualize these numbers than in standard form. But there are several opportunities for mistakes, and I see a lot of students make these. So remember, larger negative numbers are smaller. So for example, 2.1 times 10 to the negative 9th, remember, is smaller than 2.1 times 10 to the negative 8th. Also, remember that increasing the exponent by 1 increases the value of the number 10 times. And decreasing it by 1 decreases the value by 1/10. So for example, and that's another common mistake, and I know our brains aren't wired to think of it this way. So for example, 6.4 times 10 to the 5th, how much bigger than 6.4 times 10 to the 5th is 6.4 times 10 to the 10th? So logically, the first thing our brains want to say is it's twice as big. But it's way, way bigger than that. The actual answer is 100,000 times bigger. So 6.4 times 10 to the 6th is 10 times bigger than times 10 to the same number times 10 to the 5th. And then times 10 to the 7th would be 100 times bigger. And since there's a difference of 5, it's 10 to the 5th or 100,000 times larger. So just to show you how big a difference 100,000 times is, so the distance from Earth to the moon is about 100,000 times larger than slightly more than the distance of 9.5 laps around a standard track. So this is a very common mistake, and obviously it can cause really big problems. So pay attention to that. And speaking of measurement, you can go on now. We can begin section 2. Before we do that, though, let me look at the chat. Are there any questions so far? No? Okay. Well, that was meant to be kind of a quicker one anyway. So let's keep going now into units of measurements. So we'll begin units of measurement and the metric system, which is section 2. So what exactly is a unit of measurement? So, well, really a measurement is kind of anything quantitative, but some measurements are different from others because you can have discrete measurements. That's where you can only have a whole number. So for example, the number of people in a certain place is a discrete measurement because you can't have a fraction of a person. Anyway, so a discrete measurement can only be a whole number. However, a lot of measurements are you can also have measurements that are continuous. So you can have any fraction or decimal of that unit. So, so for example, with people, the exact number, the population of a place is discrete, but something like population density, that is continuous. And so continuous measurements have to be estimated by a tool or a scale. Now, one important thing is that discrete measurements often have such large quantities that they're essentially continuous. Like the number of atoms in the desk I'm sitting at. That's technically discrete. There is a finite exact number of atoms in my desk, but it's such a by our standards, ridiculously huge number that we might as well treat it as a continuous measurement. So now all measurements of continuous units are estimates. So that means the measurement is only as good as the tool that makes it. So if you measure something, say it's exactly 1 centimeter. Well, are you sure it's exactly 1 centimeter? And our eyes are a tool too. So if you take a measurement, it looks like it's exactly 1 centimeter. Our eyes can't, it might be 1.0000001 centimeter or 0.99999999999 centimeters. And plus your tool might be off, your ruler or whatever you're using to measure it. So one important thing to remember about measurements is that a measurement is only as good as the tool that makes it. And so then we get into a little bit more of a philosophical perspective, because when we say, what is a unit of measurement? Or sorry, when we say, what exactly is a unit of measurement? Really, all measurements are comparisons to a defined unit. Basically, we're saying, okay, this distance is 1 centimeter or inch or mile or kilometer or whatever. And all other measurements using that unit are just comparisons to the original unit. Now, to make it easier, you can have a group of different measurement units that can be used together and are often derived from the same place. So you can fairly easily convert between them. And when you have this kind of system, this is called a system of measurements. And there are multiple systems of measurements. But the one we're going to talk about is the most commonly used one, the metric system. So the metric system emerged from the French Revolution, and it was an attempt to decimalize the complicated traditional French measurement system. So, so in France, they had a similar system to the English units that we still use, like pounds and inches and feet. But those are really complicated. And they had other units that aren't used in the English system, but in general, it was similar. But there might be four of something in four of one unit in another unit. There might be 12 of one unit in another. It was all different types of conversions. So by decimalization, they made it so that all conversions were based on powers of 10. Now, the metric system didn't completely, the original vision of the metric system, I should say, wasn't completely, didn't completely work out, because they actually tried to do a decimal time where there'd be like 100 seconds in a minute and 100 minutes in an hour or something like that. So that didn't work out. But overall, most of the metric system units work pretty well, and they are the most commonly used system in the world. There are a few countries that don't use it very often, and we happen to be in one. But even the United States uses the metric system more than we think. For example, the American inch is actually defined as exactly 2.54 centimeters. So it's technically a metric unit, just a weird one. Now, the units of the metric system are mostly defined by the meter, but that's probably not why we call it the metric system. Basically, it was like metric, or it's like métrique, means like just measurement system. And because the meter was the basic unit, it got a name similar to that. So there are quite a few base metric units. Not sure why the size seems to have changed here. The size of my table seems to have changed a bit. Now there's actually a ton of base metric units. But the main ones, the most important ones, are listed in this table. So we have the meter, the gram, the liter, the second, the joule, and the Kelvin. Excuse me. And this is what they measure: length or distance, mass or weight, volume, time, energy, and temperature. So I put a little asterisk by gram, because gram is a base metric unit. You might hear about the SI unit system. That stands for Système International, which is basically the metric unit. But because a gram is a very small mass, they consider the kilogram the base unit. Anyway, but like I said, there are many other units that can be used in the metric system, but they generally follow this same pattern. So you have these base units. Everything could be measured in these base units. You could measure any distance in meters or any mass in grams. But since that would give you some ridiculously large or small numbers, we also use metric prefixes. So we put these prefixes, we attach them to any metric unit, and these prefixes here will act as a scientific notation power multiplier. Now, there's a lot of prefixes, as you can see here, and many of these, in fact, aren't used very often. And so in general, the most commonly used units are the base, of course, and then milli and kilo. And then that's often followed by centi and micro. But it varies depending on what the unit is. So how do we use these prefixes to create new units? So if you have two locations and they are 4,578 meters apart, you can say that the distance between these 2 points is 4.578 kilometers, in addition to saying it's 4,578 meters. So we use that prefix to convert meters into kilometers. So the prefix is, and the way this works is the prefix is essentially acting as scientific notation for the metric units. So So if we wrote the distance in meters in scientific notation, we would have 4.578 times 10 to the third meters. And so notice 4.578 is the same as the number of kilometers. So the prefix is equal to the number of kilometers, or sorry, I meant to say the coefficient. Let me fix that. I always notice, no matter how many times I read over something, I always notice a typo during the first time I'm presenting it. So notice that the coefficient here, 4.578, is identical to the number of kilometers. And the power here, 10 to the third, that is equal to the number of kilometers in a number of meters in a kilometer. So there's 1,000 or 10 to the third meters in 1 kilometer. And 4,578 meters is equal to 4.578 kilometers. And 4.578 is the coefficient when we write meters in scientific notation. So the prefix is kind of acting like scientific notation. So let's look at another example. Let's look at one that's less than 1. So let's say we have a small vial of liquid and it holds 0.0031 liters. So you can also say that this holds 3.1 milliliters. And if we wrote that volume in liters in scientific notation, we would say it's 3.1 times 10 to the negative third liters. And so once again, the coefficient, 3.1, is equal to the volume in milliliters, 3.1, and the power of 10 equals the number of liters in a milliliter. That's 10 to the negative third. So milli is 10 to the negative third of whatever. And kilo is 10 to the positive third, or 1,000 of the base unit, whatever base unit you're using. So how do we convert between metric units? So there are, there's multiple techniques you can use. A lot of times people will just move the decimal place, but I think probably the best, the method that's least likely to cause you to make a mistake is called dimensional analysis or factor labeling. And so yeah, that's probably the best way to convert between units. I always say it's the way you're least likely to make a mistake because it sets up the units in a way that it's easy to catch mistakes. So I'm going to explain this in words, and then we're going to go through some examples. So in general, the way this works is we take a measurement in one set of units, and then we multiply or divide that by a conversion factor to change the units of the measurement. So the conversion factor is derived from what is called a statement of equality. That is the number of one unit there is in another unit. So for example, there's 1,000 milliliters in 1 liter. So that would be a statement of equality. And we can use that statement of equality to make a conversion factor when we write the number of one unit divided by the number of other units. And so we use the numbers that are in the statement of equality. So the original measurement then is either multiplied or divided by the ratio. And we always set it up so that the number of units of the original measurement is in the denominator and the number of units of the desired unit are on top. So yeah, it doesn't sound very clear in words, so let's look at it with images. So for example, if we had 5 kilograms and we wanted to convert that to grams, how would we do that with factor labeling? So we start with our statement of equality, which is 1 kilogram. 1 kilogram equals 1,000 grams. So our conversion factor then could either be 1,000 grams over 1 kilogram, or 1 kilogram over 1,000 grams. And so in our example here, we're starting with 5 kilograms. We're starting with kilograms, and we want to know what the mass is in grams. So which of these conversion factors should we use? I'll jump over to the chat. Does anybody want to take a guess? Which of these two conversion factors? The first one. Yes, thank you, Aaron. So yes, because we're starting with kilograms, we want to end up with grams. So we put grams on top and kilograms on the bottom. That's why I say factor labeling makes it hardest to make a mistake. So yeah, so this is how we would set it up. 5 kilograms times 1 gram, 1,000 grams over 1 kilogram. And so that would be 5 times 1,000 divided by 1, which is 5,000. So in summary, we can say in given units, like a certain number of given units, times the desired number of desired units in one given unit equals the number of desired units. So let's try the same kind of conversion, but it's reversed. Instead of grams to kilograms, instead of kilograms to grams, it's grams to kilograms. So with 882 grams, how many kilograms is that? So again, the statement of equality is the same. 1 kilogram equals 1,000 grams. So that means we have the same conversion factors, same possible conversion factors. So which one will we use this time? Thank you, Jalen. Yes, the second one is what we use. Otherwise, it's the same basic setup. So it would end up being 882 times 1 divided by 1,000, or 0.882 kilograms. Now, one common mistake I see here, and I see this kind of mistake all the time, is there's technically 2 ways we can write the statement of equality, and they both will work. So with our 1,000 grams equals 1 kilogram, we can say that, that's true. But we can also say 1 gram equals 0.001 kilograms. So technically, there are 4 conversion factors we could use. You can use 1 kilogram over 1,000 grams, or 1,000 grams over a kilogram. But you could also do 1 gram over 0.001 kilogram, and 0.001 kilogram over 1 gram. Both of them work pretty well. But I always suggest using these conversions, the ones with whole numbers, because in general, that's easier for people to understand. But I've seen a lot of students get thrown by that. And actually, I don't see it as much with the ones that are bigger, but with the smaller units. So like a milliliter, there's 1,000 milliliters in 1 liter. We could also say 1 milliliter is equal to 0.001 liters. And I do see I see people make that mistake a lot. So keep that in mind. Try to use the conversion factors that are whole numbers. Now, one quick thing to notice is if you look at the 2 conversion factors, they're really the same thing. They're just one's one has both sides divided by 1,000. Basically, I solve the other. You can solve either one of these for 1. That's why it works. Now, I also wanted to mention that dimensional analysis works well for converting between measurement systems. So the imperial inch, which became the American inch, is defined as exactly 2.54 centimeters. I mentioned this earlier. So that means technically we are on the metric system. But assuming it's not the same system, the English or imperial system, we can still use the same dimensional analysis method to convert metric to English units. So my example is 6.5 centimeters. How many inches is that? So we do the same way. The statement of equality is 1 inch equals 2.54 centimeters. So we would do 6.5 centimeters times 1 inch over 2.54 centimeters. So it's essentially 6.5 times 1 divided by 2.54, and that gives us 2.559 inches. Now, a couple other things about conversions that I wanted to mention is oftentimes you'll have to do multi-step conversions, or multi-step conversions are the least confusing way to do it, at least. So how would we convert 53.4 millimeters to centimeters? So you can convert millimeters to centimeters directly. There's 10 millimeters and 1 centimeter. But if you don't know the conversion factor, another technique is to convert millimeters to meters and then convert meters back to centimeters. So in this case, you'd multiply by 2 conversion factors. We'd start with 53.4 millimeters. We'd multiply it by 1 over 1,000, 1 meter over 1,000 millimeters. And then immediately we'd multiply that by 100 centimeters over 1 meter to get centimeters. So if you look at how I set this up, we have 53.4 millimeters times 1 divided by 1,000. That gives us meters, 0.0534 meters. And then multiply that by 100. And divide by 1, and we get 5.34 centimeters. Now, one exception I wanted to point out is converting. The difference is how you convert between Fahrenheit and Celsius. And Celsius is just Kelvin minus 2 plus 273.15. So we're not going to talk too much about that. But conversion between Fahrenheit and Celsius is a little bit different because we must consider the fact that 0 degrees Fahrenheit is not equal to 0 degrees Celsius. So yeah, so 0 inches is equal to 0 centimeters, and 0 pounds is equal to 0 kilograms. But 0 degrees Fahrenheit is not equal to 0 degrees Celsius. So we have to, in addition to multiplying by or dividing by a conversion factor, we also have to add or subtract 32 to account for the difference. So when you're converting Celsius to Fahrenheit, you take your temperature in degrees Celsius, you multiply it by 1.8, which is the conversion factor, and then you add 32. And when you convert Fahrenheit to Celsius, you take the temperature in Fahrenheit, subtract 32, and then divide by 1.8. So notice that these conversions are exactly the opposite of each other. So for Celsius to Fahrenheit, you multiply and then add. But for Fahrenheit and Celsius, you subtract and then divide. So it's the exact opposite direction. Anyway, so that is the end of part 2. Are there any questions? No? Okay, well, let's get on now to part 3. So these are 3 measurement tools that are graduated. They have volume measurements written on them. That's what I mean by graduated. And let's say we wanted to measure 50 milliliters of water. Which of these 3 tools is best and which is worst? So let's go through each of these. So we're starting with a beaker. This is a beaker. It says here it's accurate to within 5%, plus or minus 5%. So if we measured 50 milliliters of water with this beaker, we go up to this line here, between 640 and 60. The actual volume will be between 48.5 milliliters and 52.5 milliliters, because 2.5% is 5% of 50. So that's a fairly large range of uncertainty. So let's go on to a graduated cylinder. So it is said, if you look closely, it's said to be accurate to within 0.05 milliliters, or 0.50 milliliters, sorry. So if we fill this up with water to the 50 milliliter line, we would know that the actual volume would be between 49.550 milliliters and 50.50 milliliters. So that is a smaller range than the beaker. So the graduated cylinder is more accurate. Now let's go on to this. This is called a volumetric flask. This volumetric flask is said to be accurate to within 0.05 milliliters. So you have this etched line here on the top. It's said to be 50 milliliters. So if you fill water up to that 50 milliliter line, that means your actual volume is between 49.95 milliliters and 50.05 milliliters. So that's the smallest range of actual possible volume. So remember, all measurements are estimates, like I said, and a tool is only as good as a measurement is only as good as the tool that made it. So that means that all measurements have uncertainty, but some measurements have more uncertainty than others. And so we can look at this. We saw the range of uncertainty shrinks as we go from the beaker to the graduated cylinder to the volumetric flask. So we can say that the volumetric flask is 10 times more accurate than the graduated cylinder, and that the graduated cylinder is 5 times more accurate than the beaker. So in general, if you have a volumetric flask, that's the best thing to use to measure a volume. Now, the thing is, those are only set to certain volumes, so that, and graduated cylinders aren't, so that makes graduated cylinders more useful in a lot of situations. But basically, my point here is that proper measurements will show how much uncertainty comes from the equipment that you use to make the measurement. So the way we show how accurate a measurement is by writing the number with significant figures. So when we're writing a measurement to show significant figures, we can we show all the certain digits of a measurement and the first uncertain digit. So together, those are the significant figures or digits. All later digits that come from your measurement are considered insignificant. The uncertainty figure is often listed on the measurement tool, but sometimes you have to determine it from a measurement scale. And now one thing, just because you hear this term a lot, significant figures is very frequently abbreviated as sig figs. So let's use our 50 milliliter measurement of water to figure out how many significant figures we should write. So if we measure 50 milliliters of water in this beaker, we know that the actual volume of water is between 48.5 and 52.5 milliliters. So therefore, only the 5 is certain. 0 is the first uncertain digit. And so 5 and 0 are the only significant figures. So we would write this, to show significant figures, we would write this as 50 with a decimal point, but nothing written after it. So because there's a decimal point written, we understand this measurement as having 2 sig figs, and that the actual volume is between 45 milliliters and 55 milliliters. Now, technically, this beaker is a little more accurate than that. Remember, it's only 47.5. Oh, I just realized another typo. It's 47.5. But you want to, so technically, it's a little more accurate than the way we wrote it. Where'd it go? Sorry. But in general, we want to underestimate our accuracy and not overestimate it. So let's try it now with this graduate cylinder. So because the graduate cylinder is accurate to within 0.50 milliliters, 50 milliliters of water measured with this, I swear this always happens when I'm giving a presentation. The 50 milliliters of water measured with the cylinder is between 49.5 milliliters and 50.5 milliliters. Therefore, the 5 and the 0 are certain, and the third digit, the first one after the decimal point, is the first uncertain figure. So therefore, this measurement would have 3 significant figures, and we would write this as 50.0 milliliters. And we would understand that to be saying that the actual volume is between 49.5 milliliters and 50.5 milliliters. So how about now this volumetric flask? It's accurate to within 0.05 milliliters. So if we measure 50 milliliters of water with this, the actual volume is going to be between 49.95 milliliters and 50.05 milliliters. So in this case, the first 3 digits are certain, and the 4th digit is the first uncertain digit. So we would have 4 significant figures in this measurement. So if we measured 50 milliliters of water with this tool, with this volumetric flask, we would write that we have 50.00 milliliters, and we would understand that the actual volume is between 49.95 and 50.05 milliliters. So basically, we have 2 sig figs for the beaker, 3 for the cylinder, and 4 for the volumetric flask. So I showed you as an example, but here I'll write out now what are the rules for writing significant figures. So all non-zero digits you measure are significant. So if a non-zero digit is not significant, don't write it. So zeros at the beginning of numbers are never significant. So for example, 0.0005521 has 4 significant figures, not 7. Zeros at the end of a number with a decimal point are significant. So if we had 0.000552110, that would be understood to have 5 significant figures. So this 0 is significant, but these aren't. So now zeros at the end of a number without a decimal point are not considered significant. But if it does have a decimal point, remember they are. So for example, if we wrote 1200 without a decimal point, that has 2 sig figs. But if we wrote 1200 with a decimal point, that has 4 sig figs. Now, this is a common cause of confusion. Because what if you measure something that to be 120 or 1200 of whatever unit, but it has 3 significant figures? In that case, the best way to clarify that is to use scientific notation, because all digits in the coefficient of a number written in scientific notation are significant. So 1.20 times 10 to the third is how you would write this if there were 3 sig figs. So one good mnemonic device, because a lot of people forget if there's a decimal point or whether or not there's a decimal point and which one makes zeros on the right side significant. One way to remember this is sometimes called the Atlantic Pacific rule for numbers with significant figures. So if there is a decimal present, you would start from the Pacific or left side of the number, and the first non-zero digit is significant. If the decimal is absent, you start from the Atlantic or right side, and again, the first non-zero digit is significant. Now, what happens when you add and subtract measurements that use significant figures? So when you add and subtract measurements, you'll end up generating digits that aren't significant. So to account for this, we must round a sum or difference to the correct number of significant figures. So with addition and subtraction, your answer must have the same number of decimal places as the number added or subtracted, the numbers you're adding together, with the smallest number of decimal places. And so if your sum or difference has too many decimal places, look at the first insignificant digit. If it's 0 to 4, just drop it. If it's 5 to 9, drop it and increase the last significant digit by 1. So here are some examples. If we add 8.3 centimeters to 11.571 centimeters, we get 19.871 centimeters. But the measurement with the smallest number of decimal places only has 1, 8.3. So we would have to round 19.871 to 1 decimal place, or 19.9. So in summary, 19.871 has to be rounded to 19.9 because 8.3 only has 1 decimal place. And with a difference, and remember, subtraction is really just addition of negative numbers. That's a story for another day. So if we have 12.459 minus 9.81, we get 2.647. But because 9.81 only has 2 decimal places, we have to round our answer to 2 decimal places. So that was addition and subtraction. What happens when you multiply and divide measurements, which you end up doing more often because of conversion factors and the like? So it gets a little more complicated than this, but I'll go through the simple version. So again, you end up generating digits that aren't significant, and this happens all the time with multiplication and division. So again, we have to round, but in this case, the answer, the product or quotient, has to have the same number of significant figures as the number multiplied or divided with, the factors or dividend/divisor. Going back to my middle school math vocab words. It has to have the same number of significant figures as the number multiplied or divided with the smallest number of significant figures. And so again, if yours has too many significant figures or too many decimal places usually, look at the first insignificant digit. Again, if it's 0 to 4, just drop it and everything after it. If it's 5 to 9, drop it and increase the last digit by 1. So for example, if we multiply 45.7 by 2.149, we get 98.2093. But because 45.7 only has 3 significant figures, we have to round our answer to 3 significant figures. So 98.2. It rounds down because it's a 0. Now, if we do 105 divided by 3.4491, we get 30.4427, and it actually keeps going. But because 105 only has 3 significant figures, our answer has to have 3 significant figures. So we would round to 30.4. Now, sometimes you're going to have combinations of operations, like when you're converting between Celsius and Fahrenheit. So let's look at this answer. So in this one, we first have to do what's in the parentheses. So we do 36.9 minus 32, and then divide that by 1.8. So first we do the part in the parentheses, which is subtraction, and follow the subtraction rules. So the answer is 4.9, but the least number of decimal places is in 32. It has none. So our answer has to be rounded to none. So it rounds to 5. And then we divide that 5 by 1.8 and get 2.7 repeating, but the least number of sig figs is 5. So we would round it to 1 sig figs. 5 has 1 sig fig. And so we'd round 2.7 repeating to 1 sig fig, and we get 3. So it's very important to remember the order of operations, or PEMDAS, remember that? So parentheses exponents really should be like multiplication over division and addition over subtraction, because multiplication division are done at the same time, and so is addition and subtraction. But this is where the order of operations becomes very important. So in measurements are a very important and very frequently used tool for science. They're absolutely essential for chemistry and physics, and really even for the less math-heavy sciences. Physics is probably the most math-heavy. Chemistry is after that, then earth science, and then biology. But biology even uses math quite a bit. So measurements, and again, math is based on measurements. So that's from the perspective of science. That's why measurements are important. So remember, measurements are only as good. Basically, the main things I want you to take away from this are measurements are only as good as the tools that make them. So significant figures are needed to show how good the tools are. And finally, remember the sig fig rules for arithmetic with measurement are necessary so that one does not claim calculations that are more accurate than they really are. This does happen in science quite a bit. Someone said, I found the exact mass of this, but there was something wrong with one of their tools and it throws everything off. So everyone, thank you so much for coming and good luck with your courses. And I will take any questions. Oh yeah, so Sherry, you'll be using these kind of things a lot.